All right, the drama continues here with matrixology. We're into the second of our three major blocks that make up the course. There's sort of a fourth piece as well. And it is an exciting time, people. So we are going to talk about vector spaces in this piece. Just a very brief introduction, basically. And this an enormous sort of realm we could explore here, but we're just going to talk about it in a basic way, set up the right ideas, and then we'll get into what it means for numbers in boxes. All right. I know you're excited. You should be excited. That's okay. It's good. All right. So, paging Dr. Vector Spaceman. This is how you pronounce this term. So we're going to have a new plane. So it's AX equals B, right? That was kind of the threat from the start, that we would just talk about this one equation over and over, right? 2x equals 4. Gone mad. And we're going to have a new plan. We have a new plan. So we're going to get deeper and deeper into it. The previous piece was all about getting to this triangle times a triangle equals a rectangle, LU decomposition, which is very workmanlike. It helps us solve these AX equals B problems by helping us tell computers what to do, which is the current state of things, right? So that's all very exciting, but we're going to look at this in a much deeper way, and our knowledge will become profound. All right, once again, the monks have told us what to do, and they say you must go to vector spaces. All right, so this is going to be a little introduction, and then we're going to go through we're going to unlock these various vector spaces that are attached to A and A transpose. It's all beautiful. Yes, many good things are coming. Okay, so the thing we want to go back to start with is the column picture, which I said was a big deal all the way through. So here's just an example, A and B, just 3x3 system. And what are we doing? All right, so when we solve AX equals B, it's x1 times the first column, x2 times the second one, right? We've labeled them here, A1, A2, A3, and x3 times the third, and we add these up. We have to figure out how to add these up or multiply them by these little dials, the x's, to get our B. We realized that it's possible there are no solutions, it's possible there's just one solution, and it's possible that there are infinitely many solutions. So we're going to see how all of that works in a much, much deeper way. We will understand pivots and those sorts of things, and also in a much deeper way. All right, so that's been the game, right? How do we combine these column vectors? And you can think about we're trying to create B, and the analogy I've given you is these are musical sounds, and you're trying to make a sound here, right? So there are volumes of these: viola, ukulele, and accordion. You might want to put 0 for all of them, but that's you're being asked to add them up. All right, so the new idea is we're going to understand where these vectors live, right? So we know that these ones here, for example, live in 3 dimensions. But there's something more we want to say about that, like which part of 3 dimensions, right? It could be just a plane in 3 dimensions, for example. And we need to know where the A's live, the column vectors, where the B's live, and where the X's might live, right? Okay, right. All right, and we'll be talking about rectangular matrices more as we go through this. So that sort of thing will open up. Okay, so these are, I just want to, right, there's no point in, I mean, we have to go through things slowly so you can understand them, but I might as well put the words in straight away. So these are the spaces we're going to get to. We're going to be talking about vector spaces and subspaces. We'll get to that just in this little piece. So just so you know the words, so we're looking for the null space of A, the column space of A, the row space of A, and the left null space of A. It turns out that the null space is the right null space. So these two are connected, and column and row space are connected. And the beautiful connection is between A and its transpose, A transpose, right? So this AT thing here, which we just introduced. And eventually we'll come back to AA transpose, the multiplication, which, as we understand, gives us a square matrix, and A transpose A, another square matrix. Big deals. All right. This is a more abstract piece. We'll have examples that we work on as we go through, but this is traditionally a harder section of the course, so you must, as a grasshopper, concentrate. Okay, so let's just start thinking about vector spaces. And as I said, they can be pretty general and abstract, and we can carry on, but here's just a very basic one. So, and there are different ways to write these things down, but let's just think of the plane, right? The idealized plane. So here's an example vector space. And I'll introduce some notation. Idealized plane. Right, so it's just this character here, boom, and we'll have some vectors in this. And so let's say this is x1 and x2. Okay, yeah, right. And so just some example vectors, fine. These guys are all okay, and we'll call it, well, I guess that can get confusing. Yeah, but all right, just vectors, okay? And this is a 0 point, 0 vector. We can add these things together. Right, very nice. We can stretch them. So maybe, right, stretch, so there's addition. These are exciting things you can do with vectors. Addition, stretch. And that's not how you're supposed to. So stretch has, there's stretch and shrink. Insert Seinfeld reference, and flipping. They're all to do with multiplying. If you multiply by -1, it flips over to the other direction and so on, right? So these are just some basic things we can think about. So the notation for this, we'd say, I'm going to write a big V for vector space, for vendetta, and we'll say in this case it's r squared. That's also our notation. We'll be using a lot of this, right? R to the m, r cubed, lots of this. Okay, so that's going to be a big deal. So x1, x2, it's a vector, very exciting. And then we can put, this is okay, sometimes a semicolon. Have our correct writing. And we're really saying that these are real numbers. Okay, so let me annotate that a little bit. So these are real numbers. And this is really, this is true. R equals R to the 1, right? So this is R squared, this is R1, just the real numbers. So we're allowed to have any real number here and any real number here. Pretty fantastic, yeah. Okay. All right, so this is an important notation, right? So we've got the curly braces. If you don't do this, it all falls apart, right? Nice little box, it's in it. This piece tells you the structure, and these are restrictions. So this is the basic structure here, and these are restrictions, if any. Okay, very excited for you. So there are some, there'll be some surprising vector spaces that I'll mention in a little bit, but let's go through the key, I know I've mentioned them here, but the key aspects that are pretty obvious, right? So there are two pretty obvious. It's not a good word, obvious. I've railed against that word for a long time, and even appears on the title of the book now. But yeah, I was walking along, I remember this distinctly, Canberra, maybe 1990, just going on about what a terrible word it is. Because people generally use it to mean, they usually invoke it for things that are not obvious until you know what they are, right? So trivial is another one like that. Right, the joke for mathematicians is, it's not limited to mathematicians, is it's a professor, I don't know why I'm telling you this, but a professor writing on a board and says trivially, and then pauses and then looks out the window for half an hour and then says, yes, trivially, right, okay. So, not a good word. So, but in this case, I'm going to say, presumably we've got this far with the math, this should be pretty good. So, two pretty obvious features of vector spaces. Now we're not going to get, we're going to use vector spaces. They're a big deal. They matter to us. We're just going to think about it Euclidean ones, right? The good old line, plane, 3 dimensions, 4 dimensions, which is too hard for us, but trust, 4 dimensions is just a list of 4 numbers. Okay. But some people will get very excited about vector spaces. You can keep it in a box here, all right? Okay. So 2 pretty obvious features of vector spaces. One, well, let me just say it like this, so that they are closed. Maybe this is closed under multiplication, scale multiplication, and addition, right? It's pretty obvious when we think about Euclidean ones, right? So the point is that if you add 2 vectors together, you get a vector that's still in the vector space. And if you multiply one by a real number, I won't name the people who I was walking with. They're pretty cool people. Okay. All right. Maybe I shouldn't have said it. Okay, so let's see. So this is the way. This is the formal way we'd write this out, right? So, and we'll have to do a little bit of this, a little bit painful. The subspaces part is the interesting thing here for us. But let's get the If we add any 2 vectors, words, 2 vectors in V, right? We get another vector that's still in V. So that's closed. That's it. Yeah, you can't escape. That's still in V. And 2, right? So yeah, and if we multiply, so we'll write them this. If we multiply, really is silly, isn't it? A vector V, a vector in V by a scalar. And so the scalars can be they can be different things. They can be different things, but usually for us, right, it could be a complex number, for example. For us, real numbers. A real number, right? We pull a real number out of a bag. The result is still in V. I know, this is just thrilling. I always feel like, I mean, this is setting up some bedrock, though, of course, right? The result is still in V. So, and so the picture we have here, I've really illustrated. So, right, you multiply this by a real number. Real numbers, can't be infinite, right? So it's going to stretch it, flip it the other way. It's still going to be in the plane. Add any 2 vectors together, the result will still be in the plane. A charming result. Claim. Okay. So, really simple things. Right, so we could just, this is kind of nuts. So we have 3 and 4, plus, let's do this, 773 and 6. That's fine, right? That's going to be some number, 776 and 10. You would say this is an element of R2. This is an element of R2, and this is still an element of R2, right? We can't escape. You may be thinking, why are we doing this? So this is element of. I've forgotten my structures here. This should be there. Is an element of. It's a bit of an epsilon-y thing. Fine, you're like, yeah, that's incredible, dude. So, and the other one is just, right, so 7 times 3, 4 equals 21, 28. Right, it's a number, we're multiplying it. This, let me be very clear here. This thing is an element of R squared, and this is still an element of R squared. This character, the 7, is an element of R, right? It's a real number. Real numbers. All right, so let's see if we can confuse ourselves completely. So this is starting, so we'll start to get a little bit to subspaces with this next statement. But I want to say things like, okay, so this is true. Examples of things that are and R naught, right? That R, there's actually a cat here. I really wanted the cat to hang out here, but he left. Okay, and R naught. He's a fan of matrices. Pratchett, good cat. Examples of things that are and are not vector spaces, where you would find Spacemans. So here's a few examples, right? So, well, here's a fun one, right? So let's say you can, we could have, let's say our vector is this. I'm just going to write a vector as this. It's just an example one, right? So 3 donuts plus 4 apples. That's vector 1. Vector 2 equals 2 donuts plus 1.3 apples. So basically it's x1 and x2, right? But if a donut makes sense and we can add them, then you should be able to do this, right? Then this is sort of fun. I'm being a little silly, but this is fun, right? So we would say our vector space is all donuts and apples. Put a little thing on that. Okay, right, and a little stack, whatever that means. But it's okay, you can kind of add them together, right? If we added these two together, we'd get 5 donuts and 5.3 apples. All right, that's good. You could have teaspoons or sporks. That's good. So that's 1. Yep. And then 2. Let's oh, there are a couple. So there are some funny ones. So for instance, you would write it like this. So V is all functions that are of this form, right? So just try not to confuse everything. So we have c2x squared plus c2x plus c1. So functions, polynomials of order 2. And I'll use this notation as well. Okay, so let me explain what that one is. That's just a big bar here, right? This is a such that. I like this one actually. Such that. Conditional on, sort of works for probability. Okay, so it could be this, where, and you'd say C1, C2, and it should be a C0. Oh, I've gone the wrong way. Sorry. What horribleness. That's a C1. Let me do it like this properly. Eek. So C2, C1, C0 are elements of the real numbers. Right, if we add 2 of these functions together, yeah, we could add 2 functions together, we get another one. So f1x equals 2x squared plus 3, and f2x, I know you're getting excited now, minus 7x squared plus 3x plus 4, right? We can add them together. That's still a polynomial of order 2. It's never going to pop out of that box. So this is going to be minus 5x squared plus 3x plus 7. And really this is the same as 3 dimensions, right? It's like 3 dimensions. This would be, you could think of this as your, it's a bit confusing now because we're at C's, but this could be our x if you wanted y and z, if you wanted to use your 3D thing. So a polynomial of order 2 can be represented as a point in 3 dimensions. Right? Okay. We're adding, if you multiply a polynomial of order 2 by a number, then it's still such, right? So that is awesome. Okay, that's pretty good. So what about some other things? Yeah. Okay, so try this one. Think about this for a second, but I will blather the answer. So let me write it like this. We're going to gray out this part. So it will be, and this is x1 and x2. So it will be this. I'll claim it's a vector. Let's see. So it's x all vectors, x1, x2, such that, so x2 can be anything. So what we're going to say is these vectors out here. So this is forbidden. It is a netherworld that you may not enter. All right, so there's this. And so x2 is an element of the real numbers, but x1 is greater than equal to 0. Another way to write this, just an alternative, is minus infinity. I mean, you could do this too, right? But this is x1 is greater than equal to 0. So is that a good vector space? Well, let's think about some things you can do here, right? So you can add, we can add them together. Right, so let's add these two together, for example. Boom, right? So that's good. And you can think about this if x1 is always at least 0, and then you add two vectors with that property, that's still true. So addition, so we observe the addition works. Right, so if V1, in this case, right, so if V1, you write like this, if V1 and V2, I'm just saying it, are in V, then V1 plus V2 are in V. So what we'd say is that this is they stay in the right half plane, including the 0. What else, right? So you could stretch these things. Right, so we can stretch these things. So I can multiply this by some number. Let me just give you a different vector. Here. Whoop. Well, that's hard for me to do. Why is this not exactly like paper? Okay, so we could stretch it, multiply by some number, right? Maybe a number smaller than 1. But here's the problem, right? So you can multiply it by a negative number. And that's where the badness happens. So the scalar multiplication fails. And if you want to show that something doesn't work, as is usually the case with math, if you want to show something doesn't work, you just have to show one example. If it doesn't work universally, you just have to show one example, right? So minus 3 times 1, 1. This is a good vector. It's in it's in the positive right half plane. Equals minus 3 minus 3. This one, this is in V. This is not in V. That's a sad little thing. It's not in V. Right? So that's no good. Neither is what I just wrote. And this is the problem. We can make a negative number. All right, good. So it's a bit funny because we're defining it within a space as well, right? We're already in a plane. So this is actually where we're actually starting to talk about subspaces. So note, we're really talk about subspaces. So to prove that something works, you have to show that it generally works. You have to use x1s and x2s. You have to use an abstract formalism. You can just write down anything, any one example that will fail if you want. If you want to prove that things are not working. So, okay, another example, kind of a long. So you can certainly have a case where one rule fails and the others are okay. So another example would be, I don't know if I'm actually numbering these. Yeah, all right. So this is 3, this is 4. So this is not good. So this is actually not a vector space. Let's label that clearly so that no one gets any bad ideas. So we'll say all points, and points and vectors are the same thing, right? So all points on the axes of R2. So by that I mean, right, so here's R2. Right, so any vector on these, on the axes. Something we haven't talked about yet is 0, but properly, but we'll get to that. So we can see that the scalar multiplication works, right? So if you multiply any of these vectors, any vector along the x1 axis, then it will stay there. If you multiply anything on the x2 axis, it will remain there. So we now see scalar multiplication works. Scalar, too many words, multiplication works. But, and hopefully you can see this, but addition fails. Right, so an example might be 1, 0, right, just the, plus 0, 1. And that's equal to 1, 1. So this is not in V. Right. And these ones are element of V, and this is an element of V, right? That's on the x1 axis and on the x2 axis. Okay, right, and that's what's happening here. We're gonna add these two together and get this. It's off. Right, excitement. So subspaces are going to be pretty simple for us. They're going to be pretty simple, but we have to write down some rules and kind of struggle with this a little bit. Here's one strange example, perhaps. All m by n matrices form. Right, so look at this. All m by n matrices form a vector space. Take one matrix and add it to another one, still there. Multiply by a number, still there. So that can be useful. We won't worry about it too much, but that could be useful. And it's really equivalent to r to the power of mn, which is very potentially a high dimensional space, right? Okay, think about that one. Okay, think about this. What about the integers? Right, all integers. What about the real numbers, the rational numbers? What about the all real numbers? So you add integers together, you still get an integer. You add rational numbers together, you still get rational numbers, but they fail. So they fail because of the scalar. So this is the scalar multiplication, because we always multiply in this game. We're always going to multiply by real numbers. So that's a no. That's a no. A real number times a real number is still a real number. So yes. Good. Nutritious. All right. And then here's a last one for you, and then we'll sort of just lay out the rules. All right. So 9 is what I'll call 9 today is what about this thing here? Let's put 2 examples. So these are really important. Let's say this line here and this line here. So one of them clearly is trying to go through 0. The 0 vector, this is x1, x2. I know you're just thrilled by this. Let's say this is 1 and this is 1. Right, so this is the line x2 equals x1 plus 1. And this is the line just simply x2 equals x1. So what do you think? What's a vector space? You have to think about what it's embedded in. So the vectors here are, for example, like that's a vector, right, that lives in this space. There's another one. So these actually fall apart pretty badly, because if we add these two together, right, it's clearly off it. And if you multiply this by some number, clearly off it as well. Actually, let me make that in grid. So that's going to be off as well. But the goodness is over here. So this is a no, nope. And this one is a yes. And it's because it goes through 0. It's a, right? So this is a line in 2D. So this one's okay. If we add any 2 vectors that are sitting in this they're in this line, we're still going to have a vector that's pointing in the same direction as the line. And if we multiply a vector along this line with any number, it's going to stay there, right? We're just going to, okay. So that's really important, and that's basically what we're going to generalize, right? So we can have r to the 32 and a subspace of 16 dimensions as long as it goes through 0 and looks like 16-dimensional space. It's fine. So for 3 dimensions, for example, a plane is a subspace as long as it goes through 0, and a line will also be a subspace as long as it goes through 0. So let's just write down the general requirements of a vector space and then a subspace. And okay, so I'm going to do that in the next piece. This is kind of the setup for the ideas. I'll do that in the next piece. It turns out there are many criteria, but we'll just really focus on 3. Okay, the excitement continues.